So Bill mentioned that some things do not change over time, at least in the area of circuit design. By the way, we've had a lot of changes in this area of circuit design. In fact, you have heard that we have gone from, let's say, many years ago, at least when I started my undergraduate program, we were at 0.8 micron technology, that's the gate length. And today we're talking about 18 angstrom. So we have gone a huge factor, thousands smaller in terms of size, and we've gone through from planar CMOS to FinFET, but some of the concepts are still the same. And in fact, I'm going to walk you through some of those in this talk. So the title of this talk is From Simple to Super Source Follower. And I would like to start by telling you a little bit about myself. So this is the format of the presentations, to just do a self-introduction. I already mentioned to you that I'm working at the University of Toronto, but what I'd like to highlight here is my professional fun activities. And the two that I'd like to highlight is writing articles for the Solid Circuit magazine. There are 4 issues every year, and I have a pleasure of writing one article in every one of those issues, and those are titled Circuit Intuitions. And these are meant for undergraduate students. So if you do not know about them, perhaps I have them and the reference at the end, you can look into them. And the other fun activity for me is really this event, Circuit Insights, that we've been organizing for the last few years, and I've had a pleasure of participating in all of them. So let me start from a very high perspective, and that is what is electronics and what is circuit design that we are talking about. You can think about electronics usually from the devices that you have in your pockets, whether this is your cell phone or your smartwatch or anything else for that matter, your laptop. But if you go down in terms of what is the actual electronics, what is that we do as circuit designers, is this statement that essentially electronics is the art of controlling electrons. This is what we do. And we control electrons not just because we're engineers and we like to control everything. It's just because of particular reasons. We control electrons for one of 4 main reasons. And I'd like to highlight them here. One is that we use electrons, or we control electrons, in order to store information. Everything that we remember, whether that's a picture, a photo that you take, or this talk that is being video recorded, all turn out to be bits. And we need to store those bits. And we use electrons to store the bits. Essentially, we are storing electrons, but electrons are translated to bits for us. The other one is that we use electrons in order to do information processing. And what do I mean by this? So for example, you have a signal right now, like say my voice, but then there's some noise in the background, and then you would like to eliminate the noise. You're trying to process information, and that process is happening through use of electrons. We're using resistors, we're using capacitors, and they are meant to, in fact, apply that Laplace transform that we learn in math. We're using electrons to implement mathematical equations. And then finally, we communicate information. And that is when you talk on your cell phone, when you chat on your cell phone. We're communicating information, but through what means? Through electrons. So what we are really doing is that we're controlling electrons for one of these 3 purposes. And I have 3 pictures here to show you, in fact, this is what we're doing. On the left side, maybe I use the laser pointer. Yeah, so on the left side, you see what is called a DRAM, 1 transistor, 1 capacitor memory cell. What we are doing is that when we want to store a 1, we put a bunch of electrons into this capacitor, and then we trap them. How? By turning off this valve. So we put some electrons, and if there's enough of them, we consider 1. And if you release it and bring it outside, it will become a 0. And that is how we store 1 and 0, 1 bit. And now you have millions and billions of these in your pockets. In fact, today, multi-gigabits of memory in order to store all those bits. Then we said we are going to process information, and that is through, for example, elements such as resistors and capacitors. And soon we will show you that transistors, in fact, is the main element that we use for all these information processing. And then we communicate information, and that is through, for example, a power amplifier, that you will take electrons and then we will bring them to a higher voltage, higher frequency, and then we would allow them to escape the antenna and go into the electromagnetic wave through the free space and reach on the other side. And on the other side, these electromagnetic waves are going to excite the antenna on the receiver side. They're going to create current. That current is a flow of electrons. You take that into a voltage, and then you turn them into voice and you can hear it, or turn them into a video and you watch them. And what is circuit design in all of this? You as circuit designers are actually at the center of this universe. What you're doing is that you know how to control electrons. And then there are many applications who require your knowledge. For example, if you want to build a memory, you can use memories all over the place. Somebody may come and tell you at the system level, I need this many bits, I need this type of write time, this type of read time, and they go to you as a circuit designer to actually build that memory. We talk about, for example, wireline communication. That is when you have two chips that are sitting next to each other. Bill already mentioned that the sizes of these chips are becoming so large that you can't fit them into one die. So we need to build multiple dies, multiple chips, and they have to communicate. That communication needs to be done at the circuit level. You need to control electrons in order to make that communication happen. So they will go to you as a circuit designer. They ask you to do this. Somebody comes up with a communication protocol in communication theory, and they will need to go and implement it. Implementation is through the use of electrons and transistors. And so they go back to you at the middle of this chart. You talk about machine learning and AI these days. We all know how to use ChatGPT, but you know that behind every ChatGPT today, there's multiple GPUs, many computers, and all of those are hardware. And what are they doing? They're controlling electrons one at a time in order to accomplish what we see at the end. What is amazing is that all of this is hidden from us. We don't actually see that. We are hiding our knowledge and information from an average user who is just taking the cell phone, make a call, not realizing what is going on behind the scenes. We talk about computer hardware. Computer hardware is all done by circuit designers. There are many areas. So for example, human health that we are not covering in this session today, but you can see them in other circuit insights that we have put on the web. But what I'd like to highlight for on this slide is that today we're going to cover two talks that are related to the core fundamentals in the middle, and that is my talk and Nagar's talk that will come next. And then we are going to, our two colleagues in industry, and they're going to talk about focusing on wireline transmitter and wireline receiver. The whole point of those two talks is that if I have two chips, let's say one is a CPU, one is a memory, and they need to read from the memory or write into the memory, how does that work? Because we're talking about a speed that is typically in gigabits per second per lane. And if you have multi-lanes, it can easily go to hundreds of gigabytes per second in terms of communication. How does that happen? What are the challenges in that area? And that will be covered by a colleague, Noman and Miguel. And in the afternoon, we're going to talk about wireless communication. That will be Harish from Columbia University. Okay, I did mention about circuit intuitions, and I just want to highlight that there are many articles written in this series that is geared towards undergraduate students. I would invite you to please look at those perhaps at your own spare time later. But what I want to do today in my talk is that I have taken some of those articles and I want to summarize them for you in the next 40 minutes or so that I have in this talk. And each of these items, by the way, is an article on its own. In fact, this is a 4-part article starting from the concept of a simple voltage follower, going to flipped voltage follower, super source follower, and class AB super source follower. So I'm going to walk you through this. Hopefully you have a good understanding of what is going on in these voltage followers, why do we need them, and so on. But to provide you the background for this, because I do understand we have some students in the audience who are even second-year undergraduate, some are third-year undergraduate. I want to make sure that we're all on the same page. So I like to start from fundamental. In fact, there is, this is the fundamental. This is one of those things that, as Bill mentioned, will never change. Thevenin and Norton equivalent circuit will never change. Some of you may have seen them in your first-year undergrad. and the second year. And for some reason, some of you forget about those, because when you get to transistors, they talk about the pi model and T model, and you feel that, okay, we're done with Thevenin and Norton equivalent circuit. But I would like to mention to you that no, absolutely, you still need Thevenin and Norton equivalent circuit. So let me just say what is Thevenin and Norton equivalent circuit, at least from my perspective. What I see is that if you have a linear circuit, and I'm just going to assume that that linear circuit for now consists of resistors, dependent sources, and independent sources. And if it's connected to a load, and that load could be linear or nonlinear, the purpose of equivalent circuit is to take this circuit that may have many resistors, like say tens or thousands, and have many dependent sources, and I would like to replace this with a simple connection of two elements only. One is a voltage source, and one is equivalent resistance. What I claim is that any circuit that you have could be simplified into the one shown in blue. And then as for the load, we just don't touch the load. The load stays where it is. So I will look in the circuit and I turn it into series combination of these two elements. Or I could take them into a parallel combination of a current source and a resistor. And that equivalent resistor turns out to be the same equivalent resistor as you see here. And in fact, I've used a notation here when I call this open circuit voltage. The Thevenin voltage sometimes is called open circuit voltage, and I will explain to you why we call it open circuit voltage. And in this case, I call it short circuit current. It turns out that opening circuits and observing voltage, or shorting them and measuring the current, is a great way to characterize the circuit. In fact, these are the two. If you just do these two, then you know everything about that linear time invariant circuit. So here is in a nutshell, if I am giving you a linear circuit with resistors and dependent and independent sources, what I ask you to do is first disconnect the load, make it open circuit. Once you open circuit it, you could go and measure it, or if you have the actual circuit, you analyze it, you find out what would be the voltage that you observe here, right? What have I done? I've only disconnected the load, and then you measure the voltage here. I call that voltage open circuit voltage, VOC, as a function of T, okay? So that's step one. And step two, you get rid of all the independent sources. So if you have a voltage source, you need to zero it, short it. If you have current source, you open it, and then you look into this. What you see at that point is just a single resistance, because all the dependent sources and resistors will show you a single resistance. So you can measure the ratio of V to I, and that give you equivalent resistance. Once you have these two values, then put them together, and there you have the Thevenin equivalent circuits. Similarly, what you could do, instead of opening this, you can actually short it. When you short it, you measure the short circuit current. For the equivalent resistance, you do the same, and then you put them in parallel. And these two turns out to be exactly equivalent as well to each other. Okay, now we move to transistors. That was first year undergrad that you've seen, and now we go to the second year. The transistors are nonlinear elements, but as you know, in the area of analog, we try to use them as much as we can in their linear region of operation. We try to bias transistors, especially NMOS and PMOS, as I speak about here, and that is the majority of circuit we designed today. We're going to bias them, and then around the bias point, we have linear behavior. So what I'm suggesting here is that, for example, this is an NMOS transistor with gate, source, and drain and the body, and we have the PMOS transistors. Both of these in the linear region can be modeled using this. This is called a pi model. But soon I will tell you that, in fact, this pi model is the same as Norton equivalent circuit when you look at the output node or any of the nodes for that matter. So in a nutshell, what is a transistor in linear region, or a small signal analysis? It consists of two elements. One is a dependent current source, GM times VGS, and one is output resistance. So if you bias a transistor and then only look at it in terms of a small signal behavior, this is the model we have. These two parameters are very important. We talk about GM, which is known as the short circuit transconductance. Transistors are really transconductance. You apply a voltage, you get a short circuit current at the output. The ratio of that two is GM, and then you have the output resistance, RO. For the purpose of this talk, I'm going to ignore the body effect, just to simplify things a little bit. So in general, we may have an effective GM, which is GM plus the body effect, or GMB, and that will make it slightly different, but we can just ignore it. In fact, when you go to FinFET, and we may not have much of a body effect anymore anyways, so I thought it would be appropriate for us to ignore this. So given this is a model for a single transistor, and again, you've seen it, what I would like to do is then go into another article in that series, and in fact, this was the first one published back in 2014, and nothing has changed since in this area, is looking into a node. And the idea is that when you have a circuit, you have many nodes, right? If you look into a node, what does that mean, looking into a node? Looking into a node means finding either the Thevenin equivalent circuit of that node or finding the Norton equivalent circuit of that node. Why? Because everything before that node, if you have your supply or your signal source at this end, right? And the signal propagates and comes all the way to this node, you can cut it at that node and say, what do I see behind this, right? And then you have your load afterwards. And what you see is always Thevenin or Norton equivalent circuit. So I like to move in that direction. And by the way, when we say looking into a node, there's two things that you see when you look into a node. One is the signal source, which is a Thevenin voltage source or Norton current source. The other one is the resistance. That resistance essentially is telling you what is the path to ground from that node all the way to ground. And that is specified by a resistance. So with that, if I start with a single transistor, and again, I'm only looking at small signal analysis, when I look into the gate of a transistor, what do I see in terms of resistance? If the gate and if the source and drain are small signal ground, essentially I see infinite resistance because the gate is separated. You do have a capacitance, but in terms of resistance, it's infinity. What happens when you look into the drain while the other two are grounded? Then you see RO of the transistor. And when you look into the source, you see 1 over GM in parallel with RO. And if you assume that 1 over GM is much smaller than RO, essentially you see 1 over GM. Similarly, this is called diode connected transistor. Looking into the drain, when it's connected to the gate, you see also the same type of resistance. What that tells you is that in summary, if you have a transistor, you have 3 main terminals, right? You have gate, drain, and source. If you look into the gate, you see infinite resistance. If you look through the drain, you see RO. If you look through the source, you see 1 over GM. 3 different resistances, one being infinity, very large, one being relatively large, let's say RO, and then one being relatively small, which is 1 over GM. Just to give you some concrete numbers that I like to use in this talk, I'm assuming that RO is around 25 kilo ohm, and I assume that 1 over GM is around 1 kilo ohm. So these are the numbers we're dealing with. We have infinite, 25K, and 1K ohm, right? That's what we consider. Now, what happens when you put a resistor in series with the source and you look into the drain? What it turns out, and again, please look at that article if you want to see the derivation, is that when you look into the drain, essentially you see what was at the source, but multiplied by GM-RO. But the number that I gave you for 1 GM and RO, GM-RO is about 25. So what it means is that if you put a resistor into the source of a transistor, when you look from the drain, you're taking that effectively multiplying it by 25, and you see it at the output, right? So this is the job of a transistor. Transistor is acting like a resistor multiplier. You put a resistor in the source, it gets multiplied by 25, and now you have much larger resistor as opposed to building that resistor linearly. Looking into the source is doing the opposite. If you put your resistance into the drain and you look into the source, effectively you're dividing the value of that resistor by 25, by GM-RO in this case. Now, this is the real circuit. You not just have this is connected ground, you have a signal source at the gate. And now when you look at the drain, what do you see? As I said, now that you look at a node, you see either a Thevenin equivalent circuit or Norton equivalent circuit. I've listed both of them here. The open circuit voltage become minus GM-RO-VN. R equivalent is given by this. It's essentially RS times GM-RO. And you have the short circuit current that you can easily find by dividing these two together to find I short circuit. On the other hand, when you look into the source of the transistor, you will see the short circuit current, R equivalent, and the open circuit that is given by these values. By the way, when we have a final exam for our third-year undergrad, I will provide this as a part of a cheat sheet for them so they remember what they are. You don't need to memorize any of these, but I think the concept is important that what we see is always a Thevenin or Norton equivalent circuit. Okay, I want to go give you one more tip here as we move forward, and then we're ready to go into the voltage follower. So when this often happens that you have a circuit with a signal source that's somewhere, and then you're going to find the voltage of a node. Sometimes it's very easy to find the voltage of a node if you take that node and you short it to ground. It's kind of counterintuitive because you want to find a voltage and then you short it, you have no voltage anymore. But then you measure the short circuit current in that case. And then this is what I've shown here. So you want to measure the voltage of this node, you short this node to ground, you measure I short circuit, and then you open it again and you measure R equivalent of this, and you multiply these two. And magically you get the voltage of that node. This is not really magic. This is the Norton equivalent circuit that we just saw before. So when you want to find the voltage of a node, short it to ground, measure I short circuit, multiply by R equivalent, and you're done. And to show you how easy this is and how important it is, just look at this example. I have 4 different voltage sources, V0, V1, V2, V3, with different resistors, and I want to find out what is V out in this case. Now, you may be tempted to write KCL here and solve it and do it, or you can do what I mentioned. Let's just short this to ground. If I short this to ground, this guy goes away. 8R is no longer here because it's shorted. So what do I see as the short circuit current? Is V3 divided by R plus V2 divided by 2R, V1 over 4R plus V0 divided by 8R. That's very easy to see, right? And the next step is find out what is equivalent resistance. And in fact, you can see here that if I start from here, you see 8R in parallel with 8R is 4R, 4 with 4, 2, 2 and 2, 1, 1 and 1/2. So you have this, and then you multiply the 2, and you will see effectively the digital to analog conversion that is happening. This is in fact a digital to analog conversion from input to output. Here's another example. Now includes transistors, and if you are asked to find out what is, if I have a small signal V in here, by the way, you see that the drain are connected to ground. These are AC or small signal ground. So we're only looking at small signal analysis. And I have these transistors, the value of GM and R are given to you, and also for this transistor. But we want to find out what is the voltage of this node. And what I like to do is to short it to ground. And if you short this to ground, you don't see any of the circuit on the right. You essentially see this single transistor with its GM going through this. So you can find out that I short circuit is given by this. And then you need to find out what is R equivalent looking into this, which is given the library element that I mentioned earlier. You will see RO3 here. You can find out what is R equivalent 1, R equivalent 2, make them all in parallel, and you multiply, and you get the answer. So that's the basic premise of what we talked about. All right. So with this, let's now go into the voltage follower concept. So what is an ideal voltage follower? A voltage follower that is ideal has an input resistance that is infinity. Why infinity? Because if I have a voltage at the input and I would like to transfer that voltage to the load, I don't want to load the input signal, because the input signal may have its own input resistance. And if I put any resistance in front of it, there would be a voltage divider. It will steal part of the voltage that I was planning to send it to the output. So we like to design a circuit that has infinite input impedance. That's our first goal. And at the output, when we have the load, we're going to put the load here, we'd like to have an output impedance that is 0 ideally, because we want to transfer all that voltage to the load. Again, remember, if you have any resistor here, there will be a resistive divider formed here, and that is going to steal part of your voltage. And we like to have a voltage gain that is 1, because this is supposed to be voltage follower. You apply a voltage to the input, you will like the output to follow the input. So it's very simple. We like to have a voltage gain of 1, because we want it exactly to follow it. We don't want any gain. We want infinite input impedance, because we don't want to load our source. And we like to have 0 output impedance, because we don't want to have any voltage drop across across this, okay? Now, in an attempt to do this, our first step is to just go with a simple voltage follower. So this is a simple voltage follower. Again, you've seen in your undergrad, hopefully, but if not, you will get it here. So I would like to find out that for this amplifier, for this follower, when I have an NMOS transistor, this is a bias current that I have, and this is the load capacitance that I put here, assuming that my load is capacitive. So what is going to be the gain from voltage from V in to V out? We are interested in finding that gain, that is the buffer or the voltage follower gain. And as I mentioned earlier, all we need to do to find out what is V out, we can do in two steps. First, short it to ground. Now, if you short just to ground, you see a single transistor Vn times Gm of this is going to give you I short circuit. So I short circuit is GMVN. You can easily see it. You don't need to write any equations for it. And then the next step is to find out what is R equivalent looking into this. And again, I'm looking at very small frequencies, so this CL can be ignored. What is the resistance looking into the source? We said that is 1 over GM, or RO in parallel with 1 over GM, if you don't want to ignore RO. And so then what we do is just multiply these two, and you get V out over Vn, which is GM divided by GM plus 1 over RO. Now, if you take the number that I mentioned earlier, GM being 1 kilo ohm approximately, and RO being 25 kilo ohm, GM is much larger than 1 over RO, so you can ignore 1 over RO, and you get a gain of 1. But if you don't have that relationship between GM and RO, if RO is not much larger than 1 over GM, then you get a number between 0.7 and 0.8. So we do not get exactly a gain of 1, but we get a gain of about 0.8, okay? But one more thing is not that we're just not interested only in this. We said this is one of the properties. We said we want infinite input impedance. Does this circuit has infinite input impedance or resistance? And the answer is yes, because it's gate of a transistor. That's perfect. What about the output resistance? The output resistance that we see here seems to be RO in parallel 1 over GM. And again, we said if 1 over GM is much smaller than RO, we get 1 over GM, which is about 1 kilo ohm. Is 1 kilo ohm small enough? Definitely is not 0, but it depends on your load. If your load is 100 ohm, then 1 kilo ohm is very large. If your load is 1 mega ohm, maybe it's okay, right? Because then you don't lose much in the voltage division that you have. So what we want to do is essentially try our best to reduce the value of output resistance in this voltage follower. So again, this voltage follower works. It's very simple. It's a single transistor with a bias current. It does provide a gain of approximately 1, maybe 0.8, a bit lower. It has infinite input impedance. It has an output impedance, which is 1 kilo ohm. But I like to improve this. And this is what we go instead to the next level. But before I do this, let me just show you briefly what the waveform will look like at a DC plus AC. So here's the input that I applied to this voltage follower. You can see I have a swing of about 200 millivolt, and it's sitting around 0.8. Because you're going through the transistor and you need a VGS, there's a voltage drop, DC voltage drop here, and that is bringing it down. But you have essentially the same waveform at the output. You can see that in this case that I've simulated, the amplitude is gone from 200 millivolt to 140 millivolt. So a factor of 0.7 is not a factor of 1, but nevertheless, I get it. If you look at the output versus input voltage characteristics, you will see that ideal was this. We wanted for every input voltage that we apply, we get the same at the output. So this is the ideal characteristic. But when we use NMOS transistors, this is what we will get. We'll see that we lose 0.4 volts here because that's the threshold of the transistor that we can operate on. And then once we get a slope of 0.7 instead of 1. So that's the deviation from ideal case that we get here. So as I mentioned already, the problem with this is that this output impedance, which is about 1 over GM, is sometimes too large for the loads. And so we like to see if there are methods to reduce R equivalent. And by the way, reducing this R equivalent is also helping us with the bandwidth of the amplifier. As you know, it's always the RC time constant at the output node in this case. And if you have a CL that's coming from the load, the output resistance here, the larger it is, the slower your circuit will become. So we like to solve this problem through reducing R equivalent at the output. And that is the solution that someone came up with many years ago, and it's called flip voltage follower. Instead of having the current source at the source of this transistor, you would bring it to the top. This is called flipped. So you're essentially flipping the current source from bottom to top. And what is happening here is that this current now is fixed. It's going through M1. The bias current of M1 is now fixed. You notice that here, the bias current of M1, or the current of M1, cannot be fixed because it needs to share its current with the load. Here, it doesn't share the current with load. The current just goes through M1. The current through M1 is fixed. So that means M1 is doing a great job of voltage following. And then what happens for the current, you get this voltage and you create M2. M2 is the one that is providing the current. So we've divided the job of voltage following and current delivery. We've given them into two different transistors. And again, we will see that shortly. So we can see this through finding out what is the voltage gain here. And then, of course, we'll find out what is the short circuit current. And then we need to find out what's the output resistance. So in terms of short circuit current, let's find out. If I want to find out V out, I need to short this to ground. What is this ISC in this case? What you find out is that if I have a voltage here, such as Vn, the current that you will get through this transistor is 0. Why is it 0? Because this current essentially going to the gate of this transistor, which is open circuit. So you get 0 current through I1, right? But because you have the gate of this connected to ground and you have input, which is Vn, you must have a GM-Vn current here. That GM-Vn goes through the internal resistance of this transistor and creates minus GM-RO-Vn. So essentially, you have what is called intrinsic voltage gain of this transistor. We apply Vn here, and source is grounded. The voltage it creates for you, in this case VD1, is going to be minus GM-RO times Vn. Now you apply GM-RO to this transistor, and it gets multiplied by another GM. And so the short circuit current here becomes not GM-Vn as we had before. We get GM-RO times GM-Vn. And you remember GM-RO was a factor of 25. So all of a sudden, the short circuit current is multiplied by 25 compared to what we had before. What about the output resistance? Okay, we're going to need to go to the next slide. To find out the output resistance here, I apply a voltage source here, and I need to measure the current. Again, for the same reason, the current that goes up is 0 because it ends up at the gate of this transistor. But the current that goes down, if I have Vx here, this Vx is going to translate to GM-RO Vx coming here, and that is giving me GM times GM-RO, and that will be the current. So if I divide that Vx by I2, I get an equivalent resistance that is not 1 over Gm, is 1 over Gm divided by GM-RO. So that means I reduce the output impedance by the same factor as I increase the short circuit current. If you multiply the two, you get the same. You get a gain of 1, right? You get approximately the gain of 1, but through a different mechanism. This time, you reduce the output impedance by a factor of 25. You increase the short circuit current. You increase the short circuit current by a factor of 25. And so we managed to reduce the output resistance by a factor of 1 over GM-RO. And this is the major improvement that we get from this one additional transistor. So if I put this together, and you can see this in this slide, this is the simple voltage follower. The voltage gain was, I'm explicitly showing you what is the short circuit current or transconductance times the output resistance is GM times 1 over GM, approximately. When we go to this GM becomes GM times GM-RO, and the resistance become 1 over GM divided by GM-RO. And that is what we accomplish through going from simple voltage follower to flip voltage follower. We are now getting closer to the ideal voltage follower that we talked about earlier. In fact, if you look at these, you see that the simple voltage follower and flip voltage follower showing you the same DC characteristics. But if you look at the transfer function of them in terms of the frequency, the simple voltage follower gives you a bandwidth of 1.2 gigahertz for the values that we simulated from. And when you go to the flip voltage follower, you go to 6.2. We've increased this by a factor of 5. And that factor of 5 in our design kit came, in fact, from the reduction of the output resistance by a factor of 5 when we went from simple voltage follower to a flip voltage follower. Now we can go and improve this and go to, or it's not necessarily improve, but to change this. We use an NMOS transistor here at the bottom to provide the current. We could have used a PMOS transistor instead. So we can go, instead of this red NMOS transistor, we can put a PMOS transistor on top. In both cases, you note that the voltage of the drain of M1 is feeding into the gate, right? And here also, the voltage of the drain is feeding the gate. But this is a PMOS transistor, and that's what is on the top. So this is called super source follower, but really there's not much difference between the two. And I mentioned that this is your own exercise, so you can do the same thing. First of all, try to find out what is the short circuit current, and you find out that the short circuit current is exactly the same as before, because when you short this here, you essentially have this voltage being amplified going here and by GMRO, and your short circuit current goes up by GMRO. When you find the output impedance, you find out it's also reduced by GMRO. So it will be the same equations that you have for flip voltage follower. Again, if you put them all together, you find out that there is no difference, much difference between super source follower and flip voltage follower. They're kind of giving you the same result, but except that in one we're using PMOS, in one we're using NMOS. Now, can we take advantage of both? Why don't we put both NMOS and PMOS together? So this was the flip voltage follower with the red NMOS. This was the super source follower with the green PMOS. Why don't we use both? In fact, if you use both, the circuit looks a bit more complicated, but you essentially have this circuit. And this is known as Class AB super source follower. And in fact, this circuit is being used a lot these days. I look at many conferences, including CICC and IICCC this year and last year, and you can find this circuit showing up everywhere, because this is the only way you could go to improve the situation. So let's see what happens in the case of Class AB super source follower. Again, I'm going to use the same technique, short circuit current times the output impedance, and that gives me the intuition and insight into how this circuit works. So let's start with the short circuit current. If I short this to ground, I want to just do a bit of a redrawing here, because this circuit may look complicated, but if you think about it, this VN has its source connected to ground, right? Okay, so I can just take this black transistor and put it here. The source is grounded now, it's gone. But what about the drain? The drain goes to the gate of PMOS and to the gate of NMOS, and that means this. And you can recognize this is an inverter. And that was what Bill mentioned, that maybe most circuits have inverters. So we do have an inverter here, and this is the equivalent circuit when you look from input to the output, short circuit current. By the way, if I want to find out this short circuit current, I should really add I1, I2, and I3. But it turns out again that this I1 ends up here in the gate of a transistor, so this contributes 0 to the short circuit current. It's only I2 and I3. This is why when I take this and I put it at the input, I'm not making any mistakes. In fact, this is correct, right? So let's find out, if I go from here to here, the gain, which is intrinsic voltage gain of the transistor, is minus GM1RO1 times VN. And now what happens to the short circuit current? When this voltage is applied to the gate of the NMOS, this current is going to be GM of this transistor times this, right? So that will be GM3 times GMRO. This will be GM2 times GMRO, and they add up. So I short circuit becomes GM1RO, which is the first transistor, and then it gets multiplied by GM2 plus GM3 times VN. So our short circuit essentially increased not just by a factor of GMRO, but also by a secondary GM. So essentially we have another factor of 2 compared to what we did in the case of super source follower, for example, right? We just said that GM is multiplied by GMRO. Now GM is added to another GM, NMOS and PMOS, factor of 2, and then multiplied by GMRO. So this is the summary. I said the transconductance is twice that of FEF and SSF, or essentially is the sum of the 2. Now, what about the output impedance or output resistance in this case? So again, let's do this experiment. I have the circuit here. Obviously, I need to zero the source. Whenever you want to measure the output resistance, you need to zero your sources. So if I zero this and I apply a voltage here, Vx, well, I'm going to see what's going to happen. Again, I want to redraw the circuit because it's fun when you do this, because you can make it more intuitive. So this transistor M1 has its gate connected to ground. Its source is now connected to Vx, which I connected here. The drain, though, goes to the gate of PMOS and to the gate of NMOS. And again, you can see them here, gate of NMOS and PMOS. And that is exactly the inverter that we talked about. Except that now I have Vx also at the output. And so I need to find out what is the total Ix that I measured here, right? But remember, there's a Vx at the input. So the way we handle this is the following. We can say, okay, there's 2 sources. We can use superposition. You can zero one, measure the other one, or vice versa. And then also you can see, in this case, in fact, when you have this transistor going to the gate, the current here is going to be 0 anyways. So again, it doesn't contribute to any current, so I can ignore it. If I apply Vx here to the source of the NMOS transistor, I get a drain voltage, which is again GM1 RO1 Vx. And then from here, I can measure the current, which is GM times this plus GM of this times this. And if I add them up, Ix become GME 1RO times GM2 plus GM3 times Vx. We already ignored effective, so this should be really GM RO1. Now, if you divide Vx by Ix, you will get R equivalent with this, which is this. Now you can see R equivalent showing the same behavior. So we used to have 1 over GM, and when we used flip voltage follower, it became 1 over GMRO times GM. Now the GM part is two components to it, GM2 and GM3, which means that R equivalent is half of flip voltage follower and simple source or super source follower. So we did another reduction by a factor of 2 by going to the class AB. Now, the real reason, though, that we use this class AB super source follower is something to do with symmetric rise and fall time. We did not spend much time on this so far, but I'd like to explain that to you in terms of the behavior of this when we apply a large signal to our input. So if you apply a large signal to the input of this, and again, I've color-coded so you can see if I use a simple source follower, I just have the black transistor with this connected to the current source. If I use flip voltage follower, I have these extra transistor red. And if I use super source follower, I have the green added on top. But let's see what would be the behavior of the output voltage under these 3 cases. I apply a voltage that goes from 0.6 to 1 volt. Why do I start from 0.6? Because I'll make sure that the transistors are on. Otherwise, you remember that we have a bit of a dead zone first when we apply the voltage to this. But if you look at the first one we look at is the flip voltage follower in this case. The flip voltage follower has a transistor here at the bottom that can really draw current as much as it wants from the load. But if you do not have the PMOS transistor, the current from the top is limited by the current source that you have on the top. So you cannot really, for the case of flip voltage follower, which is shown here, you can easily pull it down very fast through this transistor M3, but the pull-up of this node, which is happening through this current, is limited by the amount of current that you have here. This is what we call the slew rate. How fast can the output move up or how fast can the output move down. If you only have this NMOS transistor at the bottom and the current source, the rate that goes up, which is the slew rate for the positive signal, is going to be limited by the current source. And that is shown here. You have a limited slope that it goes up, right? But when you want to pull it down, you can pull it down faster because you have a transistor. Now let's look at the green case when we move to super source follower. Now we have a transistor that is coming from the top and is going to provide you as much as current as you want. And so by going to the super source follower, you can increase the slew rate going up because you have a transistor that can do this. But again, in that case, we had a current at the bottom, and that bias current is going to limit how fast it can go down. So in this case, the falling edge is slowed down. When you put them together, you have both NMOS and PMOS transistor, and you can pull it up fast and you can pull it down fast. So the circuit becomes more symmetric in that sense. Okay, so here's the summary of what we talked about. We said that the voltage followers that we have, we like to have ideal voltage follower, but in practice, we could use simple voltage follower, we could use flip voltage follower, super source follower, or class AB super source follower. What is the difference between them in terms of voltage gain? Well, ideally, we like to have a voltage gain of 1. But in all of these cases, we get approximately 0.8, somewhere between 0.8 to 0.1, to 1. We can live with that. That's not a major issue. Input resistance in all the cases are infinite, so we're really close to ideal case. But when it comes to the output resistance, we like to ideally get to 0. If you use simple voltage follower, you have 1/GM, approximately 1 kilo ohm with the numbers that I gave you. When you go to this, you get 1 kilo ohm divided by 25, so you get 40 ohm. From 1 kilo ohm, you go to 40 ohm, much closer to 0. When you go to super source follower, the same thing happens. And when you go to the class AB, you get another reduction by a factor of 2. So now you get 20 ohm, from 1K to 40 to 20. What about the slew rate? I said in the ideal case, the positive slew rate, or rising edge slew rate, and the falling edge slew rate should be identical, and that would be this. In fact, the only one among all of these that satisfies this is the class AB super source follower. For the other ones, these two are not equivalent, and the circuit is not fully symmetric. And I guess this is for this reason that you can see this last one appearing a lot more in the literature today as we move forward. This is the list of references that I've used for this, but for the full list of circuit intuitions, I've actually put them up on my own website, so you can go into this and you can find the last 41, I believe, articles that I've written for you in this category. Bill mentioned already some of the SSCS resources, but I want to highlight some of them that is most relevant to the talk that I provided to you. Solid circuit magazines, if you look at all issues, there are actually at least 3 articles that are very accessible to all of you. As I mentioned, I write the circuit intuitions, but my colleague Bezal Rezavi from UCLA, he also writes a series. Every issue is called The Circuit for All Seasons and the Analog Mind. The level of that talk is a little bit above undergrad, but still accessible. So if you're starting graduate students, I would highly recommend you to look at those. And then we have a colleague from Analog Devices, Chris Mangelsdorf. He is writing an article from industry perspective. He's worked for many years in analog devices. He is very intimate with data converters and a lot of analog circuits, and he writes shop talk, what you didn't learn at school. Obviously, you like to learn those that you didn't learn at school, so you should read those articles. Bill mentioned YouTube channel of Solid Circuit Society. I provided you a link here. The circuit intuitions, as I said, I have them all in one place for you that you can look at. Circuit insights, including the recording of this, will be on SSCS YouTube channel, but I provide just the links to all of them on my own website, so for easy access, and you can look at those. In addition to all of this, there's a resource center, which is for SSCS members only, and this is why Bill was asking you, become a member of the society, and I like to highlight this. Becoming a member has been very important to my own career, and I'm sure it will serve you very well if you move in this direction. There are many tutorials, many short courses of the conferences that we just don't put on YouTube. We put them on Resource Center because They are sponsored by the society, and society would like to use them only for the members that they've helped create that content. So feel free to become a member. And as a student, you get a major discount. So you pay a small portion of what I or my colleagues are paying to use the same resources. With this, I'd like to just acknowledge members of my research group at the University of Toronto for their view of or review of Circuit Intuition's articles. I'd like to actually thank all my undergraduate students. I am teaching currently a third-year undergraduate course, and obviously the material that you see here coming because of a lot of interactions and great questions that they ask. So I try to bring those into the Circuit Intuition's articles. And I'd like to also thank the readers of Circuit Intuition's articles. I get a lot of great emails from them, great feedback, and sometimes suggestions for future articles, which I'd like to ask you as well. And finally, I'd like to really thank the Solid Circuit Society, who has been sponsoring this event and many other educational activities across the board. I think my time is over. 4 seconds, 3, 2, 1. Thank you very much.